Da da da. 6.6.6. Oh no. Let's do some homework problems, all right? We're gonna do a lot of ones in this video just to make sure that we're all on the same page. We're gonna start with number 10 from the homework. All right, that's the wrong section. We're gonna start with number 10 on the homework. And again, all of these are really just one of 4 different kinds of problems, but they can appear in a couple of different ways. All right. So this first one is going to be one of these equations where we're solving an exponential equation with like bases. All right. Goodness. So we're going to try to find the same base, rewrite it, and then go from there. So this is exactly the one. I hate it when I do this. Let's do number 8. 625 times 5 to the 3x plus 3 equals 125. So we're trying to find like bases. All of these things can have a base of 5. So what we eventually want is 5 raised to some exponent equals 5 raised to some other exponent. So let's rewrite everything with 5s. 625, that is 5 to the 4th power, I think. 5, 25, 125, 625. Times 5 to the 3x plus 3. And again, 125 is 5 cubed. You can check these with a calculator and make some guesses. On the left, we just add those exponents together. This becomes 3x plus 7 when we add these exponents together. And now we can use the one-to-one property for exponents. These are one-to-one functions, so if the functions are equal, the insides, these exponents, are equal as well. Three x plus 7 equals 3. 3x is negative 4. X is negative 4/3. Should be able to check our answer. Hopefully it works. If we plug in 4/3, this becomes negative 4 plus 3, negative 1. 625 divided by 5 is 125, so it checks out. Let's do 26. If 26 is also one I did in the videos, I'm going to lose my mind. All right, once let's solve this one. 3 to the 2x plus 1 equals 7 to the x minus 2. And again, these are the ones that you have a ton of choice on. Do we take log base 3? Do we take log base 7? Do we take the natural log, the common log? They'll all give you the same answer, but they're going to look different. So if you want to check your answer on these ones with the ones in the book, type them into calculators and make sure you get the same approximation. I want to show something a little different this time. I'm going to show, in the video earlier I did natural log. I'm going to show what happens if we take log base 3. Log base 7, common log are also good choices. Take log base 3 of both sides. Let's see what we get. So now on the left, we can use that inverse property. On the left, they cancel each other out. We're just left with something really nice. On the right, the inverse property doesn't work because they have different bases. But the entire exponent comes out in front with the power rule. This becomes x minus 2 times log base 3 of 7. Now we need to get all the x's on one side and all the numbers on the other, because this is a linear equation. So distribute. 2x plus 1 equals x times log base 3 of 7 minus 2 times log base 3 of 7. Move this over, we'll be good to go. So subtract x log base 3 of 7 from both sides. And subtract 1. So that gives us 2x minus 1x log base 3 of 7 equals negative 1 minus 2 log base 3 of 7. Well, now we factor out an x. If we factor out an x, then we can divide by the coefficient and get the x by itself. So if you factor out an x, we're left with 2 minus log base 3 of 7. And the right-hand side is negative. We could rewrite this a little bit. Let's factor out a negative. We're going to clean things up a little bit. We'll see why in a bit. Now we can divide by this whole thing. To get x is negative 1 plus, we could write this as log base 3 of 49 if we want. I don't think it really necessarily looks better though. It's personal preference maybe. Divided by 2 minus log base 3 of 7. And this is a perfectly good answer, but if we factor out a negative from the bottom, then it looks even better. We can factor out a negative from the bottom and cancel these negatives. And there's a little bit of stuff that you can do to make this look nicer, but not that much. We can have this be our final answer. Or you can play with it a little bit more. All right. I'm not gonna make you do that. It's a lot easier to clean up if you have everything in terms of natural log or common log. Should be able to check your answer here too. That's a perfectly decent answer. Again, the book might simplify it further. Just make sure that your answers are the same. Let's do another one. 34. Use the definition of a logarithm to solve the equation. 2 times the common log of 8n plus 4 plus 6 equals 10. So if you only have one log, you want to get that log by itself. So we can use the definition of a log, convert it to exponential form. So to get that log by itself, we have to subtract 6 first. And then we have to divide both sides by 2. And now remember, the common log is base 10. Converted to exponential form, it becomes 10 squared equals 8n plus 4. 10 squared is just 100. And that's just a linear equation. Subtract 4. Divide by 8. You should get n equals 12. Especially with logarithms, make sure to check your answer here. Check your answer. You get 96, and then 100. Log of 100 is 2. 2 times 2 is 4. 4 plus 6 is 10. Good. Check your answer with a calculator. Do 48 next. Log base 8 of x plus 6 minus log base 8 of x equals log base 8 of 58. Now, if we had two logs equal to each other, if we had it like this, with the same base, log base 8, then we'd be good to go with a 1-to-1 property. We have 3 logs. We need to combine these logs. We do it with the quotient rule. Log base 8 of x plus 6 over x equals log base 8 of 58. Set those insides equal to each other. All right. X plus 6 over x equals 58. Solve this equation. Anytime you have a variable in the denominator, get it out. Multiply both sides of this equation by the LCD, the least common denominator. Subtract x from both sides to get 57x equals 6, where x is 6 over 57. I think that reduces. They're both divisible by 3. X is 2 over 19. I think. Well, I don't know. I think. Let's check our answer. All right, the left-hand side is log base 8 of x plus 6 minus log base 8 of x. The question is that equal to the right-hand side, which is log base 8 of 58? Ooh, great. They are indeed equal. So we know we're in the domain. Always make sure that we're not having any logarithms of negatives. And it equals. What about 62? Solve the equation for x and graph both sides of the equation to verify your answer. Log of x squared plus 13 equals log of 7x plus 3. That's what it said, right? 7x plus 3, yep. So we're already set up for the 1-1 property for logarithms, right? One log with the same base is equal to another log with the same base. So these insides are just equal. This is a quadratic equation, so get everything on the same side. Get it in that quadratic form that we like to work with. It's going to give you x squared minus 7x plus 10 when you subtract everything over. Now try to factor if possible. Two numbers that multiply to 10, then add a negative 7. Again, if they're multiplying to a positive number and they add to a negative, they have to both be negative. So negative 1, negative 10, that doesn't work. Negative 2, negative 5. Ah, there we go. X minus 2. X minus 5. We get that x is equal to 2 and 5. But we have to make sure these are both answers in the domain. If we plug in 2, yep, that's positive. Yep, that's positive. Oh yeah, and plug in 5. All right, great. It looks like we have 2 answers this time. Well, let's check graphically. Log of x squared plus 13. When does that equal the log of 7x plus 3? Ah, they do intersect twice at 2 and 5, just like we said. As a side note, this logarithm of x squared plus 13 looks kind of weird. Doesn't look like a normal log, right? Because there's no asymptote, because we are never going to get 0 inside here. The inside is always at least 13. That's why this first thing looks kind of so bizarre. Yeah, there's still 2 intersections here. When x is 2 and when x is 5. Just like we said in our work. All right, what about 70? Rewrite the exponential expression with the indicated logarithm and use a calculator to approximate to 3 decimals. 70 is 3 times 1.04 to the 3t equals 8. Now it wants us to use the common log and then approximate to 3 decimals. So we're still going to get this exponential by itself. Get the exponential by itself. That means divide both sides by 3. Now, normally we'd take log base 1.04 to undo it. But log base 1.04 is not very nice to work with. So we're going to use the common log, like we were instructed. Common log of the left-hand side equals the common log of the right-hand side. We're solving for t. This power rule is going to say this comes out in front. 3t times the log of 1.04 equals the log of 8/3. Let's not approximate until the very end. It did want us to round to 3 decimals. But if we wait until the end to approximate, we get a much better answer. Solve for t, so divide by what's being multiplied by t. And we'll get that t is the log of 8/3 divided by 3 log of 1.04. That's what we'll type into our calculator. Log of 8/3 divided by 3 times the log of 1.04. Should be about 8.336. Let's check our answer. Let's plug in 8.336 and see if it works. 3 times 1.04 raised to the 3 times 8.336. We wanted that to be about equal to 8. Good. There's some rounding error. But yeah, it's about equal to 8. Good to go. One last example. 74. Use a calculator to solve the equation. Round to the nearest 10,000th. Tenth is 1 decimal. 100th, 1,000th, 4 decimal places. Natural log of 3 plus the natural log of 4.4x plus 6.8 equals 2. So if we get one log equal to another, we can use the one-to-one property. If we get a logarithm by itself, we can use the definition, but we have neither one of these situations. If we combine these logarithms, though, then we'll have a single log that we can solve for and convert it to an exponential form. All right. Combine these with the product rule. This is 3 times 4.4x plus 6.8. And now we can convert this. Base of the logarithms, base of the exponential. Input becomes output, output becomes input. And we can distribute that 3 at the same time. Becomes 13.2x plus 20.4 maybe. If not, we'll find out when we check our answer. Get the x by itself. So 13.2x is equal to e squared minus 20.4, or x is e squared minus 20.4, all divided by 13.2. Let's type this into a calculator. E squared minus 20.4 divided by 13.2. It's about negative 0.9857. Let's check our answer because I didn't use a calculator, so I really need to check the answer. The left-hand side is the natural log of 3 plus the natural log of 4.4 times x, which is about negative 0.9857 plus 6.8. That was supposed to be about 2. And you can see, yep, it's about 2. And we're good to go. Rounded to the nearest 10,000th, 4 decimals, just like we were instructed. All right, let me know if you have any questions and good luck.